Good morning, everybody. So how is your day going? Hopefully you are having a good one. This is already Friday, but we still have lots of things to cover. So let's start. So last time we were talking about the alternating series test, and we had a couple of we have a bunch of examples. Now, just a quick recap. We say that for the alternating series test, we consider a series of the form of this sum, right? Wherein you have a factor that causes the series to alternate in sign, and you have a separate factor an that doesn't change signs, right? So in order to apply the AST, what you need to do is to consider uh, the factor that doesn't change sign, right? And show that it is decreasing and the limit is equal to 0. If these two things are satisfied, then that means that the alternating series will be convergent. All right. Now, if the second condition fails to hold, then a nice thing is that we can argue using the basic divergence test that the alternating series is divergent. Because that means if this is not equal to 0, that means the limit of an times negative 1 to the power n won't exist because it will just oscillate between a positive value and a negative value. So by the basic divergence test, the alternating series will diverge. That's why we usually start checking this condition, and depending on the results of that limit, we can do the appropriate tests. All right. Now, do you still have questions about the application of the AST or just the AST? Because I'm thinking of doing some problems involving testing for absolute convergence, because I encountered several students yesterday in my CASA tutorials asking for help about absolute convergence. So I think that's where we can start today. Some examples about determining absolute convergence. Then afterwards, if time permits, we can go to power series. Is that a good plan? Also, if you have specific questions, I'll be happy to help you with that. I remember during the start of the semester, you guys have lots of questions, and I didn't, I eventually, I did not get enough time to go to my examples because you have lots of questions. But I noticed that lately you don't have any questions. So either you're getting better and better with Cal2, or you're just too shy to share your questions. What is it? No questions really, guys? Or you haven't tried answering the quizzes yet? All right, so if you don't want to answer my questions, then I'll proceed with my own examples here. Okay, so the instruction here is to determine whether the following series are absolutely convergent. All right, just a quick recap. Let's recall what absolute convergence mean. Recall, so the series summation of an is absolutely convergent if the series with the absolute value is convergent. Okay, this is what is meant by being absolutely convergent. This series is absolutely convergent if the series obtained by putting the terms inside absolute value bars is convergent. And the nice thing is that if the series is absolutely convergent, then it is convergent. Then it is also convergent. Okay, so this tells us that absolute convergence is a more general condition, or it's a more overarching condition, because if your series is absolutely convergent, it follows that on itself it is convergent. And it's easy to see why, because we say absolute convergence means that this series with the absolute values is convergent. But when we compare this guy with this guy, this series, the second series, is larger, right? Because it has absolute values. So we are guaranteed to always get a bigger sum in here, right? But if this is convergent and our series is smaller than a convergent series, then by direct comparison, this guy is also convergent. And that's what we have in the second statement here, right? Now, the series sum of an is conditionally convergent if it is convergent, but the absolute value series is divergent. All right. So if your given series is convergent, but the series with the absolute values is divergent, then we call this series conditionally convergent. All right. And there's an importance about absolute convergence and conditional convergence. If your series is absolutely convergent, then you can rearrange the terms, and you will get the same sum every time. But if your series is conditionally convergent, then you can rearrange the terms, and you will get a different sum. But I think that discussion would be for higher math courses. So yeah, but that's the essence of being absolutely convergent. All right. And I guess for us, the only purpose of absolute convergence for now would be for power series. But they do have much more theoretical implications. All right. So perhaps today let's focus on checking if these guys are convergent or if series are absolutely convergent or not. Let's have some examples. So, okay. Again, the instruction here is to determine whether the following series is absolutely convergent. Let me see if I have some good examples here. Okay, let's try this one. The sum of -1 to the power n plus 1 over 5n minus 1 and going from 1 to infinity. All right. So for testing for absolute convergence, I always start by looking at the limit of the positive part. Okay. Because this is basically a two-pronged solution or a double-edged sword. So if this happens to be, if this is 0, if the limit is 0, then I'll proceed with the alternating series test. Because remember, alternating series test requires us to get the limit of the positive part, and if it's equal to 0, then I can proceed to the next step, which is checking if this is decreasing, right? So if this happens to be 0, then I'll proceed with AST, and I can conclude something about the convergence of the given series. Now, if this is not equal to 0, then this series will be divergent. And the series with the absolute value will also diverge. So that means there is no chance that that will be absolutely convergent because both series will be divergent. So that's why finding the limit of the positive part serves a dual purpose for the solution. All right. So let's see. Let's take the limit as n approaches infinity. Obviously, this is equal to 0 because the denominator is will become a very large number when n increases, right? So 1 divided by a large number is equal to 0. The limit is 0, so I'll proceed with the AST because I cannot draw up any conclusions by just looking at the limit. So now I proceed with the alternating series test. But here I note that a sub n, which is 1 over 5n minus 1, is decreasing. And that is obvious, right? Because when n increases, the denominator increases. An increase in the denominator makes the fraction smaller. So an's will be decreasing. So by the alternating series test, the given series, and again, it's the given series, is convergent, right? So now if your given series is convergent, it can be either absolutely convergent or conditionally convergent. So we need to test for absolute convergence. Now test for absolute convergence. And for that, we consider the absolute value series. If this series turns out to be convergent, then the given series is absolutely convergent. If this series diverges, then we have a conditionally convergent series. Now, what's the effect of the absolute value symbol? Well, the absolute value symbol will just mean that the top will always be positive, so we'll be left with this one. Let me write that properly. There we go. Okay. So this would be the absolute series. What would be a nice thing to do here? Actually, I can do comparison test, limit comparison test with the harmonic series, but let me see if direct comparison will work here. I can make the denominator. Okay, what happens if I just ignore the -1? Say I'll have 5 over n. What would be the group inequality symbol? So here what we did is to make the denominator larger, right? So we made the denominator larger, making the the fraction smaller. So this would have been like that, but I know this is a divergent series. So this guy is smaller than a divergent series. Direct comparison test doesn't have any conclusion for us. So let's see. Well, I can do limit comparison test here because I need to know whether this series converges or not. So we use limit comparison test with the testing series sum of what? Well, the numerator is just 1. Then in the long run, how does the denominator behave? In the long run, you can ignore lower order terms. That means you can ignore the -1. So that means in the long run, the denominator just behaves like 1 over 5n, or the denominator just behaves like 5n. So essentially, this is the long-term behavior of our given series, but you can rewrite this as 1/5 times the sum of 1 over n as n approaches 1 to infinity, which is a multiple of the harmonic series. Thus making it divergent. So here the testing series is divergent, right? Now I'll do the limit comparison test. I'll take the limit of the ratio between the n term in our given series over my testing series. But the way I designed the testing series is that I know that this limit will be a constant number, right? Because essentially I analyze the given series or the series that we have. And I know that this will behave in a proportional way to this series. So that's why I know that they will both diverge. But to formalize my reasoning, I need to take the limit of the given the terms of the given series over the testing series, right? But I have an idea of what will happen. Because when you simplify this, this will become 5n over 5n minus 1 as n approaches infinity. Top is degree 1, Bottom is degree 1, equal degrees, divide the coefficients. Limit is equal to 1, which is finite. So by the limit comparison test, the summation of 1 over 5n minus 1 and going from 1 to infinity is divergent. So let's recap. What do we have? The alternating series was found out to be convergent. The absolute series is divergent. So our conclusion, the given series, what's the exponent? N plus 1 over 5n minus 1 is conditionally convergent. Again, because the given series on itself is convergent, but once we put everything in absolute values, then it will diverge. So that's why it is conditionally convergent. All right. Oh, no worries, Fatuma, that's fine. Okay, any questions for this one? Is it clear? Right. So yeah, that's right, Bao. I want always to start with an easy one before going to the more complicated ones. I hope there would be some problems that are complicated for you guys. Okay, let's try another one. Unless you have some questions, if you encountered a hard or difficult question, just let me know, then we can work them together. Let's try this one. The index doesn't matter here, but let's try this one. Now, the thing here is that my earlier approach might not be helpful here because I have factorials, I have 2 to the n. Seeing if this will be decreasing would be difficult. So, but what I can do here is to try to test for absolute convergence right away. So this is another approach. You can test for absolute convergence right away, because if it is absolutely convergent, then automatically it's convergent. So no other questions asked. So let's try testing for absolute convergence right away. So for that, we consider the absolute value or the sum of the absolute values. So we'll consider this guy, but everything put inside absolute value bars. But this is just 2 to the power n over 2n plus 1 factorial. All right. If this is convergent, then we're done. We have shown absolute convergence. If this happens to be divergent, then we need to do another test. See if the alternating series will converge, because there's a chance that this is conditionally convergent, right? But do you remember, guys, what's the method to use for series like this? You have factorials involved. So hopefully by now you know that the ratio test might be helpful for this. So I'll apply the ratio test. So let's do the ratio test. Okay. So for the ratio test, we take the limit of a sub n plus 1 over an as n approaches infinity. A sub n plus 1, we replace all n's by n plus 1. So we'll have 2 to the n plus 1 all over. Oh, be careful here. I will replace that n by n plus 1. So we'll have 2 times n plus 1 plus 1, everything inside a factorial, right? All over the given term as n approaches infinity. Okay. Now let's rewrite it as a product of two fractions. This will be the limit of 2 to the power n plus 1 all over. Let's simplify this, the thing inside the factorial. This is 2n plus 3 factorial, right? Times the reciprocal of the denominator, 2n plus 1 factorial, all over 2 to the power n as n approaches infinity. Now here's where the nice property of factorials will come into play, because you see that this is the product from, this is the product from 1 until 2n plus 1. This is the product from 1 until 2n plus 3. So you see that most of the factors will cancel out. In fact, everything here will be canceled out. But in the denominator, we are just canceling 1 until 2n plus 1. So that means in the denominator, we'll be left with 2n plus 2 times 2n plus 3. Right? After canceling the factorials, that's what we will be left with in the denominator. Oh, here 2 to the n will be canceled by most of the factors here, but there would be a 2 left on the numerator. So essentially, this would be 2 over 2n plus 2 over 2n plus 3 as n approaches infinity. Top is a constant. Denominator becomes very large, so the limit will be equal to 0, which is less than 1, right? So by the ratio test, the series that we have, which is basically this guy, is convergent. And since the series with the absolute value is convergent, then the series without the absolute values is absolutely convergent. And remember, absolute convergence implies convergence as well. So this one is absolutely convergent by the ratio test. Okay. Do you want to answer another one, or is it good? You really are very shy sending questions in. Actually, in my previous class earlier, we devoted all of our time answering their questions. So I was hoping that you will also have questions today. But perhaps you are already good at determining absolute convergence, so that's also fine. Now let's see. Okay, perhaps let's try another one. Then if you don't have any questions, I'll proceed to power series. Okay, so this one, we are given the sum of -1 to the power n times n plus 1 squared all over n plus 1 times n plus 4, and check if this is absolutely convergent, right? Since there are no factorials involved, perhaps I'll do the first approach that we have. I'll take the limit of the positive part, which is n plus 1 quantity squared over n plus 1 times n plus 4 as n approaches infinity, right? But this is equal to 1 because the numerator is degree 2, denominator is also degree 2, leading coefficient on the top is 1, leading coefficient in the bottom is 1, so the ratio will be equal to 1, right? So that means this is equal to 1, so that means the series, so this means the limit, so we cannot apply AST here, right? Because the limit is not equal to 0, but as I have remarked earlier, when the limit is not equal to 0, you can argue using the basic divergence test that the given alternating series will be divergent. Because the limit of the nth term of your alternating series won't exist. And it will not exist because this part here will go to 1. But remember, you have an alternating sign. So that means in the long run, this will either be a number close to +1 or a number close to -1. And we don't know what will happen in the long run. Actually, there's no uniform behavior in the long run. It will just keep on oscillating between a number close to -1 and a number close to +1. So that's why the limit won't exist. So by the basic divergence test, the given series is divergent. Is divergent, right? So this guy is divergent, and it follows that the one with the absolute value will also be divergent. Do you know why, or do you have any idea why that is true? So I have shown here that the alternating series is divergent. Why am I saying that it follows directly that this guy will also be divergent? Any idea? Come on, guys. Just let me know that you're still there. Not sure, not sure. Okay, so, but I hope it's clear that this guy is divergent, right? But this guy is smaller than this one, right? Because this either is positive or negative. Once I put everything in absolute value, then that means every term here is larger than the terms in here. So I hope you agree that this summation is smaller than this summation, right? Am I making sense? Okay. And this guy is divergent, so this is infinite. And so this will also be infinite because this guy is larger than an infinity. So basically that's the reasoning here. So it follows that this is divergent. So you are happy if you will be able to show that the alternating series is divergent because no follow-up question will be asked. There's no chance that the absolute series will be convergent. So that's why we stop at saying it's divergent. But if this is convergent, then you need to check if this will converge or diverge. Because if this is convergent, there are two possible cases. The series is absolutely convergent or it is conditionally convergent. All right. All right, so now you have a choice to make. Is this now clear? And do you want to proceed to power series now, or do you still have questions about determining absolute convergence? What do you say, guys? Good? Okay, that's great. Let's move on to power series. By the way, I already have uploaded worksheet, blank version of worksheet 19. Okay, which is about power series. Well, for power series, it has some distinct form. You can think of it as, say, a sub k, some constants times either x to the power k, or a sub k times x minus c to the power k. These are how power series look like, right? So the difference with the series that we are dealing with before was that now we are involving the values for x. So before we don't have any x's, right? We only have the ak's or the an's. But this time, these are power series. These are functions of the variable x. Now, the thing here is what we usually want to know about power series is the radius of convergence. So to find the radius of convergence, or the interval of convergence, we need to look for all x's for which the series converges. And the usual trick here is usual approach is to use the ratio or root test, or in some cases, we can also use geometric series. And perhaps this is more better illustrated using examples. So let's try some examples. Okay. Let's say determine the interval of convergence of the following power series. Let's start with an easy one, simple one, just to illustrate the concepts. Let's try the sum of x to the power 2n all over -3 to the power n. Okay. So what do we see here? Well, what I see here are n's in the exponent. So perhaps here I'll use the ratio test. Use the ratio test for the series with the absolute values, right? So for that, we'll take the limit of x to the power 2n all over -3 to the power n raised to 1 over n as n approaches infinity. All right. Now that's the thing. One difference between the ratio and the root test for plane series and for power series. For power series, we put everything in absolute values. All right. So you can think of it as testing for absolute convergence. Because the thing is that if your series is absolutely convergent for a value of x, say c, then it would be convergent for all x's whose magnitude is less than c. So that's why you can take the absolute value for the ratio or the root test. Okay, so simple manipulations here. I can get rid of the absolute value bars by saying that, okay, this becomes x to the power 2n all over 3 to the power n as n approaches infinity. Everything raised to 1 over n, right? And then what I can do here is distribute the power 1 over n to both numerator and denominators. So what we'll have is x to the absolute value of 2n raised to 1 over n all over 3 to the n raised to 1 over n. You can skip some of this manipulations of the exponents if they are clear to you. I'm just including them just to illustrate the point, right? Now remember, loss of exponents, if you have a power raised to another power, then you can simply multiply the exponents. And that's why the root test is nice to use whenever there are n's in the exponents. Because in the numerator, we'll have absolute value of x to the 2n over n all over 3 to the power n over n as n approaches infinity. And then we simplify the exponent, so we'll have quantity x squared all over 3 as n approaches infinity, right? And this limit will just be equal to absolute value of x squared all over 3. All right. Here, you remember, just remember that we're taking the limit as n approaches infinity. So that means x is treated as a constant, right? So that's why I got absolute value of x squared all over 3. Again, the reason is that we're taking the limit as n approaches infinity. So x can be treated as a constant. All right. Now we're applying the root test. Remember, what's the conclusion for the root test? We know that this will converge if, so the series will converge if the absolute value of x squared over 3 is less than 1. Agree? That's the conclusion of, that's the requirement for the root test, right? For the root and the ratio test, your limit must be less than 1. Okay? Now, remember, for the interval of convergence, we're looking for what are the x values for which the power series will converge. So we know that it will converge when this inequality is met. So we need to solve for those x's. So this means that absolute value of x squared must be less than 1/3. So that means we should have -1 over root 3 less than x less than 1 over root 3. Right? Or in other words, you can say that the power series will converge if x is an element of root 3 over 3 with a negative there. Oops. I should use a parenthesis here. Root 3 over 3 here, right? Because I don't, yeah. This is all what the ratio test will tell us, that it will converge if you are in this open interval. It will be divergent whenever whenever the limit is greater than 1, but it is inconclusive when x is equal to 1. So we need to do other tests whenever we are on the boundaries. That's why I had to erase the closed bracket that I was about to write and instead use a parentheses. Because again, the ratio test will be inconclusive when the limit happens to be equal to 1. And it will be equal to 1 for negative root 3 over 3 and positive root 3 over 3. So we are uncertain for those two values, but but for all other values, we know that it will diverge. So what remains to be done is to check if the power series will converge when x is equal to plus or minus root 3 over 3. Again, because the root test is inconclusive for these two x's. So we need to apply separate tests for these two guys. So let's start with the negative root. Then how does the power series look like? Remember, our power series is x to the power 2n over -3 to the power n, as in the index doesn't matter. All right. If you plug in x equals negative root 3, so we'll have root of, actually this will work for both of them because they will be inside a square. So I can merge the two solutions into one, because here I'll have root 3 over 3 quantity 2n all over -3 to the power n, right? And so this guy will be the sum of what? 1 over 9 raised to the power n all over -3 to the power n. Or basically, you can say this is the root of this is the series -1 to the power n of 1 over 27 to the power n. Do you agree? Now what happened here? I have -1 to the power n. I put that in here. And then I have 1/9 to the power n all over 3 to the power n. I can write them under a big power n, right? So I'll have 1/9 divided by 3. That's going to be 1 over 27. Okay. And this guy, what can we say about this one? Note that 1/27 to the power n is a geometric series with common ratio 1/27, which is less than 1. So the series of 1/27 to the power n is convergent, thus making the series with the alternating sign also convergent. So here we see that this series will be convergent, and this series was derived when x is plus or minus √3/3. So that means the power series will be convergent at the endpoints as well. So your conclusion, therefore, the power series has interval of convergence negative √3/3 until √3/3, and the two endpoints are included. And that's the thing, you need to do it, or you need to check convergence at the endpoints of your open interval, because the ratio test or the root test will be inconclusive when the limit is equal to 1. All right. Okay, perhaps let's try another one. Let's try sum of -1 to the power n times n all over 4 to the n of x plus 3 to the power n. N goes from 1 to positive infinity. So here I can try to use the ratio test. So let's use the ratio test. You could have also used the root test. They are equivalent. And I guess you'll have a solution of the same level of difficulty. So let's try the ratio test. We'll do limit of the absolute value of an plus 1 all over an as n approaches infinity. And this is the limit between the ratio of replacing all n's by n plus 1. Let me do that here. 4 to the power n plus 1 times x plus 3 to the power n plus 1 divided by, I'll just copy the term. As n approaches infinity. Now I can start canceling at this point. I know that this guy will be canceled by this guy, leaving us with an x plus 3 on top. So essentially what we got right now is the limit of, well, the absolute value bars will do us some wonders. Specifically, this will be canceled by this one supposedly, leaving you with a -1 on top, but we are inside an absolute value, so you can ignore that -1 there. So what do we have? We have x plus 3 times n plus 1 over 4 to the n plus 1 times the reciprocal of the denominator. So we have 4 to the n all over n as n approaches infinity. Oh, here we can still cancel some factors. 4 to the power n will be canceled by this guy, leaving us with only with a 4 here. So essentially what we're taking the limit of would be x plus 3. This should be inside absolute values because x can be negative, we're not sure. Times n plus 1. N plus 1 is always positive. That's why I can't just ignore the absolute value that would have come with it all over 4n. as n approaches infinity. Again, we're taking the limit as n approaches infinity, so all x's are deemed constants. So this guy can go out of the limit. And what is the limit of the remaining factor? So they are both degree 1. Coefficient of n on top is 1. Coefficient of n in the denominator is 4. So the limit would be 1/4, right? So the series will converge if the limit that we got from the ratio test is less than 1, right? So this means that absolute value of x plus 3 can be less than 4. Then let's solve this inequality. Get rid of the absolute symbol, absolute value symbols first. So we'll have -4, x plus 3, 4. And then we add, we subtract 3 from both, from all sides. So we got -7 here. We get x. We subtract 3, so we get 1. Right? So the series converges on the open interval -7 to 1. It will diverge from -infinity to -7 open, union open 1 to positive infinity. But at the endpoints -7 and 1, we are not sure. So we need to check what happens at the endpoints. So let's do that. If x is -7, let's see how the series look like. So if x is -7, so go back to your series. Let me just copy this over. Okay, so I will replace all x's by -7. There you go. And see if this will converge or not. So this guy will simplify to -1 to the power n times n over 4n times -4 to the power n. But we can write this as -1 to the power n times n over 4 to the n. Now I can look at it as two factors, -1 times 4. So I'll have a -1 to the power n times 4 to the n, right? Loss of exponents in reverse. Now I can cancel 4n here by the 4n there. And then we'll have -1 to the n times -1 to the n. So this will always be positive. Or perhaps if you want some details, I can write it this way. We'll have a sum from 1 to positive infinity of -1 to the n quantity squared times n. Is that right? Okay, so this will just be the sum of n as n approaches 1 to positive infinity, which is divergent. Because limit of n as n approaches infinity is not equal to 0. So that's by the basic divergence test. All right. Is that good? Now, so we know that it will diverge at x equals -7. Let's try the other endpoint. So if x is equal to 1, so we'll get our series. Okay, replace the x by 1. Then this will simplify to -1 to the power n over 4n times 4 to the power n, and going from 1 to infinity. This will cancel with that one, giving us -1 to the power n times n, which unfortunately will also be divergent, right? Because the limit of -1 to the power n times n as n approaches infinity won't exist. So what I applied here is the basic divergence test. Because the limit is not equal to 0, then it would be divergent, right? So the interval of convergence for the power series is the open interval -7 to 1. Now, it's a coincidence that in our two examples, uh, the series both converge or both diverge at the endpoints. There are some series that will be convergent on one of the endpoints and divergent on the other one. So you can see, or you might see, interval of convergence of the form, say, -7, 1, or -7, 1 included. So there are series wherein those the interval of convergence are the half open, half closed intervals. So that's why really you need to check what happens on both endpoints of the intervals of convergence. Because again, the basis test that we use, which is the ratio test and the root test, are inconclusive when the limit is equal to 1. All right. So it's already time. So what I'm going to do is probably give you one more example about it on Monday. Hopefully one which will show you a half open and half closed interval. Actually, there are also some power series that will never converge. Hopefully I'll insert another example of that before going on differentiation of power series, leading us to a discussion of Taylor series expansion. Do you think it's a good plan? Hopefully you'll come up with questions on Monday. So probably you'll have the weekend to try some of the quizzes or homework problems. Let me know if you have difficulties with them, all right? Okay, guys, that's it for today. Hope you have a good weekend. Let's see each other back on Monday. All right? Bye, guys.